Hey everyone, welcome to the second video from section 2.9. So in this video, we're going to look at the two main examples of finite difference equations. We're going to do a brief look through the linear one, which I'm going to leave most of the stuff to do tomorrow in class. We'll just take it from the book. And then we'll take some actually I'm going over the logistic equation and what kind of stuff we can do with that. We'll look at equilibrium points and some other basic analysis for that equation. Let's go ahead and jump right on into it. So first, we'll take a brief look at the linear difference equation. And this guy just has the form yn plus 1 equals rho times yn. And rho of 0 is whatever it is at this point. So all we're doing is every step we just multiply by rho. Now, so let's see what happens here. So first, equilibrium solutions. There's only one equilibrium solution here. It should be pretty easy to find. It's just yn is identically 0, right? Because if yn is 0, then so is yn plus 1, and so is everything from there on out. So 0 is the only equilibrium solution here. Now, what happens as n goes to infinity? Well, let's look at what yn is in terms of y0, right? So if y0 is just a number, then y1 is going to be rho times y0, right? y2 is going to be rho times y1, which is rho squared times y0. You can probably see the pattern here. Y to the n is just going to be rho to the n times y0. So what happens as n gets really, really big? As n goes to infinity, what happens? Well, this goes to 0 if rho is less than 1, right? Because if rho is less than 1, I'm taking higher and higher power, something less than 1, it's going to squeeze down to 0. It's going to stay always at y0 if rho is 1, and it's going to diverge to infinity if rho is bigger than 1. So in this case, I really only care about rho being positive, so I can ignore the negative 1 case where I oscillate back and forth. But so for rho positive, I either get 0 if rho is less than 1, I get a constant value of y0 if rho is 1, rho being 1 isn't really that interesting, and I get infinity if rho is bigger than 1. So what this tells me is 0 is asymptotically stable if rho is less than 1, and it's unstable for rho bigger than 1. This doesn't really make too much sense for rho equals 1, so we'll just kind of ignore that case. But we get asymptotically stable if rho is less than 1, and unstable if rho is bigger than 1. Now the reason I wanted to go over that real quick is we're going to want to use that fact for our logistic equation that we're going to go to in a second. So let's go ahead and write out that equation and see what we can deduce from there. So the logistic difference equation is going to look a lot like the logistic differential equation, but things are going to be in steps instead of being in terms of derivatives. So I get yn plus 1 equals rho times yn, 1 minus yn over k. Looks a lot like the logistic differential equation, you just have now these steps instead of the actual function itself. And what I'm going to do to make this a little easier to look at is I'm going to set un to be yn over k. So I'm just going to scale everything by k, which gives me then that un plus 1 is just rho un 1 minus un. So it gets that k factor out of the equation. And I will expand this out so we can see it. It's rho un minus rho un squared. So step 1, equilibrium solutions. So in this case, there are actually two equilibrium solutions. I get the same one from before, un is 0, because if un is 0, so is un plus 1, and we're good. There's also a second one, and the second one I get is un equals rho minus 1 divided by rho, right? Because if I want this here to be equal to un, I can just move it over to the other side and then divide through by un, and you'll get that un has to be rho minus 1 over rho if it's not 0. So we have that. Now we want to look at stability of these two equilibria. So let's first look at near 0. So if it's near 0, right, we have that un plus 1 is our equation there, rho un minus rho un squared. Well, if un's really, really close to 0, then un squared is super tiny. So we can assume, this is a sort of a linearization approximation, where un plus 1, we know this is equal to rho un minus rho un squared. But if un is really close to 0, this is really small, so this is the same thing as, this is pretty close to rho un. So if we're near 0, that's the case. But we know when that's stable. So this is asymptotically stable if rho is less than 1, and it's unstable if rho is bigger than 1. Because that was from the linear equation from before. Now there's a last step here to say that if the linearization approximation doesn't change stability, it doesn't, but there's no we can't actually prove that here. But now what about the other equilibrium point? Well, for this one we want to do something similar, but in order to do that we need to have something that's small. So we're going to let un be rho minus 1 over rho plus some vn. And since we're close to rho minus 1 over rho, then vn is going to be small. And now we want to plug that into our equation for what un plus 1 should be. So I know un plus 1 equals rho un minus rho un squared. And I want to write everything here in terms of v's instead of u's. So I get that rho minus 1 over rho plus vn plus 1 equals rho times rho minus 1 over rho plus vn minus rho times rho minus 1 over rho plus vn squared. Now, if you take that equation, you square everything out, and you simplify it, what you end up seeing is the following. You see vn plus 1 equals 2 minus rho vn minus a rho vn squared. So then, as before, this is going to be small, so we're going to get this is about 2 minus rho times vn, which means we know our stability again by the same argument from before. So this is asymptotically stable for rho between 1 and 3, because that is where 2 minus rho has absolute value less than 1, and it's unstable otherwise. Okay, so there's our stability for that point as well, which means we have what's called an exchange of stability at rho equals 1. So what do I mean by this? Well, for rho less than 1, 0 was stable, and rho minus 1 over rho was unstable. But for rho bigger than 1, 0 is unstable, and this guy is now stable, at least up until 3. So the stability moves from the 0 to rho minus 1 over rho when rho gets bigger than 1. All right, and now there is one last thing to show you before we get to the next video, and that's a way to actually compute these sort of step-by-step processes. So that involves this picture they draw in the book that I'm going to show you how it works out real quick here. All right, so here's the picture, one of the pictures I drew in the book. This is for rho equals like 3.2 or something like that. So the idea is the curve gives me the y value of the curve is rho x 1 minus x, which is the next value if I'm at the proper x value. So say I start at 0.3. So I'm starting here at 0.3. To find the value, I just trace straight up until I hit the curve. And this here will be u1, say. Now, how do I find my next value? Well, I can find my next value by tracing horizontally till I hit this line, y equals x. Now, what that does is that gets me to the x coordinate that matches the y coordinate I had before. So my x coordinate here is now u1. So if I trace this straight down, my x coordinate, which should have matched the one from before, but I can't draw straight lines, is u1 again. And now I want to drop from here straight to the curve. So this will give me u2. And I continue the same process. I go over to the line and up to the curve. And this will give me u3. So this kind of is like that stair-step process they do in the book for going from one value to the next one. And it just kind of gets you step by step closer to the solution. If I had had the actual straight lines here, this one should converge to the critical point up at that other side. And so if I were able to draw straight lines on here, this should converge to the critical point at the intersection of the parabola and the y equals x curve up at it should converge to this guy up here. And for those of you who are doing chemical engineering, because this is where I come from, you'll see things similar to this when you look at distillation columns and doing analysis like that. It'll be a similar sort of process where you go to the curve, go to the straight line in the middle, go to the curve, straight line in the middle. This is how distillation columns are generally formulated, is in that sort of process. All right, so that's it for this one. In the next video, we're going to go through what happens if rho is bigger than 3. Because if it's bigger than 3, things get bad real quick. So thanks for watching, and we'll see you in the next one.